So Jai Hind students, so this is our first lecture in the special series in which we will be covering the important topics of our subject digital system design. So the topic is circuit realization. So we will be covering basically three methods by which we can design the circuits. The first one is using the basic gates. So by basic gates we mean that we will be covering realization using AND or NOT, and then we will proceed to our realization using universal gates. So these NAND and NOR gates, NAND gate and NOR gate are universal gates. So independently NAND gate can be utilized to design any complex circuit. Similarly, independently NOR gate can be realized to realize any complex Boolean expression. Okay. So these are the three methods. So let's start one by one. So if we have to realize the circuit for Boolean expressions, first of all we have to identify what kind of operations are being mentioned in that expressions. That means if we can find that there is a bar, then that bar can be computed using a NOT gate. If we see that there is a product, then that product can be realized using an AND gate. Similarly, if you see a plus sign, or we can say that plus operator, then it is equivalent to OR gate. And further, these expressions can be of two types, SOP and POS. So if we go by SOP, in which we will see that there will be multiple products. That means you can see here that there are two products and both these products are summed together. So this is a product, and this is sum. So this becomes an SOP expression. Similarly, here you can see that it is a sum, this is another sum, and both these sums are multiplied, that means product. So this is a POS expression, product of sum expression. Okay. So if you want to draw the circuit, these are simple expressions. We can realize the circuit as per our requirement. As and when a operation is performed, we can realize that operation using a circuit component. So we can see that there is a bar. Starting with the expression, there is a bar. That means there will be A. It will be converted into a bar using a NOT gate. Then there is B. Both these are to be multiplied. Then B bar. That means this is B. Its inverted version will be computed, B bar, and then there is C. So these are the two products, and both these products will be added together using an OR gate. So this is the expression for, this is a circuit realization for a simple SOP expression. Okay. Similarly, we can realize circuits for POS expressions as well. So let's realize the circuit for this A plus B into B bar plus C. So this A plus B, that means there is a variable A, another variable B. Both these variables are to be added together using an OR gate. Then another sum is to be created, B bar plus C. That means we need B bar. So this is B. We can compute B bar and multiply it with C. So these are the, sorry, I have used an AND gate, it has to be an OR gate. So this is B bar and C sum, and both these sums are to be multiplied using an AND gate. So this is realization using realization for a POS expression. So we just need to check how many NOT gates are required, how many AND gates are required, how many OR gates are required, and that circuit has to be using minimum resources, minimum components. So the questions might be asked in two ways. You will be given an expression and you have to realize the circuit. That will be the simplest one. And if you are provided with an expression and examiner says that you have to minimize this expression first and then proceed towards the circuit realization. So this can be another way in which we will be designing the circuits. So this is basic realization using basic gates. Now covering another case for this basic gate realization, in which we are provided with a slightly complex expression. So in this we cannot proceed with the as per our, we will not be going into circuit realization as per our requirements on need basis. That means I will not be generating NOT when I require that. I will be generating all the NOTs all together. First all the NOTs will be generated, then all the products will be generated, and then finally the sum will be generated. Because this is an SOP expression in which we are having multiple products. This is a product, this is another product, this is another product. So all these four products are to be summed. Okay. So if we proceed for the circuit realization of this expression in a systematic way, because the previous two circuits which we have realized were not the systematic approach, were not covering the systematic approach to realize the circuit. Because if we are provided with a complex expression, then that approach will be generating a correct circuit, but that correct circuit will not be systematic enough to show that it is correct. It might give an impression that it is slightly clumsy or a bit complex. So examiner will not be able to evaluate properly that whether this circuit is correct or not. So there is a systematic approach. We have to identify that which are the variables for which inversion is required, for which bar is required. So we can check here, A bar is required, here we can see B bar is required, and here we can see C bar is required. So these are the, all three variables are requiring the complements. So if we start preparing the circuit, first of all we will be realizing A and its complement, A bar. Similarly B and its complement. Similarly C and its complement. So all three inverted versions are prepared. Then we can start preparing the products. The first product is A bar, B, C. So this is A bar, this is A bar, this is B, and this is C. So all these three things are to be multiplied using an AND gate. Then proceeding towards this second product, A, B, C complement. So A, this is A, this is B, and this is C complement. Another product. Third product is A bar, B bar, C bar. That means all complements. So this is A bar, this is B bar, and this is C bar. Another product. And last product is AC. So this is A and this is C. This is the fourth product. So all four products are available, and now these products are to be summed using an OR gate. So we will be taking an OR gate which will be adding all these four products. Okay. So this is a systematic approach by which we can realize the circuit. No matter how much complex is the expression, we just need to find that which variables are requiring NOT gate, that means which are in complemented form. First of all, we will be preparing those negated versions, inverted versions, and then we will be preparing the products using AND gates, and finally the sum. So all this process is valid for an SOP expression. So if the expressions get changed to POS, then there will be NOT gates first, and then there will be sums first. Then that means we will be using OR gates first, and output of all those OR gates will be fed to the input of AND gate to generate the POS version, product of sum. So this is all about circuit realization using basic gates. Okay. Now we will proceed towards the circuit realization using universal gates. So universal gates are NAND and NOR. So let's proceed for the NAND based realization, circuit realization using NAND gate. So for NAND realization, we have to first understand that whether we need to realize one-on-one equivalence of all the gates using NAND gate. That means if I need an AND gate, then I need to separately prepare AND gate using NAND gate. If I need OR gate, do I need to separately prepare OR gate using NAND gate, or is there something conversion which is directly relatable and which can save the resources? So regarding that, there is a statement written here: equivalence of AND OR realization. AND OR means SOP type expressions. Equivalence of AND OR realization to NAND-NAND. That means we are claiming that any AND OR expression or any SOP expression can be simply realized using NAND gates only by simply replacing every gate with the NAND gate. So to prove this, we have taken a simple expression y is equal to AB plus CD. So for this AB plus CD, the simpler, the basic version, basic circuit realization will be: this is A, this is B, A and B. Similarly, C and D. Okay, and there is a plus, that means OR gate. So using an OR gate, so this is a basic gate version, which is having AND gates first and there is an OR gate at the end, which is giving you the final output. So this is AND OR realization. Okay. Now I am saying that this AND OR realization can be performed using NAND only by simply replacing AND with NAND and OR with NAND. That means all NANDs. That means I am saying this. So A is there, B is there, and instead of using an AND gate, I am using a NAND gate. Similarly for C and D as well. And then instead of using an OR gate at the output, I am again using an AND gate. And I am saying that these two circuits are exactly similar. So there is no doubt in that this is AB, this is CD, and this is AB plus CD. But here we have to check that in the second circuit, this will be AB complement, this will be CD complement, CD whole complement, and this will be AB complement dot CD complement whole complement. Using De Morgan's theorem here, we can check that it will become AB double complement, dot will change to plus, and CD double complement. So these double complements will cancel out each other and the final expression will be AB plus CD. That means both these circuits are giving identical outputs. That means I can say that this AND OR realization is equivalent to NAND-NAND. Okay. So this is the basic expression which we have realized using NAND gate. Now taking slightly complex expression which is provided here. Now we will try to realize this expression using NAND gate, using the same concept which we have covered here, that replacing every gate with the NAND gate. Okay. So A, B and C are the three variables. So this is A, this is B, and this is C. Complements of all three are required. Here you can see A bar is required, here B bar is required, C bar is also required. So preparing the complemented version using NAND gates only. Okay. So these are the inverter based on NAND gates. Similarly for B bar, similarly C bar. Okay, now we can start preparing the products. The first product is A, B, C complement. So this is A, this is B and C complement. And instead of using a AND gate, I am using a NAND gate. Similarly for second product, A bar, B bar, C bar. So this is A bar, this is B bar, this is C bar. Another product, another NAND gate. Last product is AC. So this is A and this is C, another NAND gate. All three products are calculated and then finally we have to compute the sum. But instead of using the sum, as we have seen in the previous slide, in which we have said that AND will also be replaced with NAND and OR will also be replaced with NAND. So instead of performing sum of these three, we will be using NAND of these three, because we have proved in our previous slide that AND OR circuits are equivalent to NAND-NAND circuits. So this is the NAND based realization of this given expression. Okay. So this is the NAND realization of a SOP expression. But we have to keep this in mind that we have said that AND OR realization is equivalent to NAND-NAND. That means every input which is reaching the OR gate must be coming from the output of AND gate. Okay. That means only then it will be considered as AND OR realization. So if there is an expression, let's take this expression. Here you can see that this is a product, this is another product. By product we mean that this must be coming from the output of an AND gate. Okay. But there is a single variable C which is not a product. Okay. That means this third variable in the sum of these three things is not coming out from the output of an AND gate. So it cannot be termed as AND OR realization, because this third component is not the product. It is not coming from an AND gate. So to give it the structure of AND OR realization, I can simply multiply this C with C itself. Okay. That means instead of realizing circuit for A, B, C complement plus A bar, B bar, C bar plus C, I am realizing the circuit for C dot C. I can do this because it is within the laws of Boolean algebra that if a variable is multiplied with itself, it remains unaffected. But by doing this, now this expression can be visualized as in which there are three products. First product is ABC complement, second product is A complement, B complement, C complement, and third product is C dot C. Okay. But by doing this, now it is in the form of AND OR realization, and we can prepare the circuit like this. So there is A complement, B C and C complement, ABC complement, realizing this first product, ABC complement. So this is A, this is B and C complement. Then second product is A complement, B complement, C complement. So this is A complement, B complement, C complement. And we will be using NAND gates only. And the last C dot C, that means this thing. This is C, another C. Okay. And finally, so this is a third product, and finally all these three products are to be summed. So for sum we need a OR gate, but We have seen that equivalency that AND OR can be realized using NAND-NAND. So for OR gate, we will also be using a NAND gate only. Okay. So this is the expression for this. This is a circuit realization for this given SOP expression. So we have seen that SOP can be simply realized using NAND by simply replacing every gate with NAND gate. Okay. But if we are given a POS expression, and we are asked to realize this POS expression using NAND gate, then it is not that simple, because POS means OR AND form. OR AND cannot be simply realized using NAND-NAND. So we have to convert this POS type expression into SOP type expression so that we can easily realize that expression using NAND gate. So one of the approach is by simply multiplying these variables, opening the brackets, multiplying with each other, and this POS will be converted into SOP. But that will be slightly lengthier process. So instead of going into that, we are computing the complement of this expression. That means we are computing the Y bar. So if we compute Y bar, that means I am doing this, and this Y will become Y bar. So if we do this, then the expression becomes A plus B plus C complement. So this is the first sum bar. Then this dot changes to plus A complement plus B complement plus C complement bar. Then again this dot changes to plus and A plus C whole complement. Again applying De Morgan's theorem, we can see that this will become A bar dot B bar and C double complement. C double complement will become C only. Then this plus changes to plus, will remain plus, and then the second, this thing will be A double complement dot B double complement C double complement. That means A B C. Okay, and the last one will be A complement dot C complement. So this is the expression, but we have to keep in mind that this is not Y, this is Y bar. But this Y bar is very much easily realizable using NAND gate because it is looking like a AND OR expression. So we can simply go for the circuit like this is A, realizing its negated version. Similarly B, similarly C. Okay, then realizing these products A bar, B bar, C. So this is A bar, this is B bar, and then C. So first product, first NAND gate. Then second one is A, B, C. This is A, this is B, and this is C. Second NAND gate. Third one is A complement, C complement. So this is A complement, this is C complement. Okay, and all these are to be added. So instead of using OR gate, we will again use a NAND gate. But the thing which we have to keep in mind that this is for Y bar. That means this is not Y, this is Y bar. So if we want to realize expression for Y, then we need to remove this bar, which can be simply removed by using a NOT gate, which will again be based on NAND gate. So this is circuit for Y. So in this way we can see that any given POS expression can also be realized using NAND gate by first converting that expression into SOP by simply complementing it, realizing the circuit, and using an extra NOT gate to remove that complement. Okay. So this is all about NAND based realization. So we can realize any expression, whether it is SOP or POS, with single variable, multiple variables, any number of variables using NAND gates. So we can proceed towards now circuit realization using NOR gate. Okay. Again, we are making a claim here that OR and based circuits, OR and realization is identical to NOR realization. By OR and we mean that it is a POS type expression. Okay. That means POS expressions can be simply realized using NOR by using all NOR gates instead of any other gate. That means NOT will also be replaced by NOR, OR will also be replaced by NOR, and will also be replaced by NOR. Okay. So let's proceed towards this A plus B dot C plus D. So again, this is the simplest of the expression by which we are proving the equivalency of OR and NOR. Okay. So this A plus B means this is A, this is B. OR gate, similarly C and D. And then this product means AND gate. Okay. So this is Y. So this is OR, and this is AND. So this OR AND expression can be simply realized using NOR gates by replacing all gates with NOR gates. So let's try the NOR version. So this is A, B, NOR. Similarly, C, D, NOR, and finally another NOR. So we are claiming that both these circuits are identical. Okay, but we have to prove that. So we can simply check that it is A plus B. This is C plus D. And here this Y is A plus B into C plus D. Now for the second circuit, we can check. This is A plus B complement. This is C plus D complement, and this will be A plus B. This is the first input plus C plus D. This is the second input and whole complement. And applying De Morgan's theorem here, we can see that it will be A plus B double complement. Double complement will cancel out each other. This product will change to dot and C plus D double complement. So double complement will again cancel out each other. So we can see that both these expressions are identical. So this is this and this, both are identical. That means we can again re-emphasize that OR and circuits are equivalent to NOR circuits. That means OR can also be replaced by NOR and can also be replaced by NOR. So by using this equivalency, now we can realize any complex POS expressions. So let's take a simpler expression, a sample expression for POS. So we can check here that there is a sum. This is a sum, another sum, another sum, and all these sums are multiplied, product. This is a POS type expression. Okay. So this POS can be easily realized using NOR, as we have POS, or we can say this POS is also equivalent to OR AND, because all these sums, this sum is OR, this sum is also OR, it is also OR, and this product is AND. So this becomes OR AND, and in the previous slide we have seen that this OR AND is equivalent to NOR. That means OR will be replaced by NOR and will also be replaced by NOR. So let's start making the circuit. So A, B, C, complements using NOR gate. So this is complement using NOR gate. Either we can go for this one or this one. Both are not. That means if there is a single input in NOR gate, it will act like a NOT gate. So either you can draw a single input or you can merge both the inputs. Both are equivalent. Okay. So for the simplicity, I am using single input. Okay. Now preparing first sum A plus B plus C complement. This is A plus B plus C complement. Second one is A complement plus B complement plus C complement. So this is A complement, B complement, C complement. Third one is A plus C. So this is A, this is C. So 3 NOR gates have been used for 3 sums, 3 NOR gates have been used for 3 NOTs, and finally a single AND gate will also be replaced with a NOR gate. So this is the expression for this Y. We just need to keep in mind that OR AND form is equivalent to NOR form. Okay. But now again we have to keep in mind that all the inputs which reach the final AND gate, here you can see that all the inputs which reach this final AND gate are coming from the outputs of OR gate. Only then this OR AND can be equivalent to NOR. Okay. So here you can see that this is an OR gate, this is an OR gate, but this is a single variable. So this cannot be an OR gate. But we can replace this A with A plus A, which is equivalent to A only. But now this A plus A is equivalent to OR gate. Now there are 3 OR gates, and all these OR gates will be multiplied together by using another AND gate. This becomes OR AND form, and OR AND form can be easily realized using NAND-NAND. So let's draw the circuit for the same. A, B, C. This is A complement, B complement, C complement. First one is A plus B plus C complement. This is A plus B plus C complement. Second one is A complement plus B complement plus C complement. So this is A complement plus B complement plus C complement. Third one is A plus A. That means this A, another A. So these are the 3 sums, and finally product. So for product also we will use another NOR gate, because OR AND form is equivalent to NOR. So this is the expression for Y. Okay. So this is how we can realize a POS type expression using NOR gates only. Okay. But the last, again a glitch. Now if you are asked to realize a SOP expression using NOR gate, this is not very simple, because SOP can only be realized using simply NAND gates, and POS can be realized using NOR gates by using one-on-one replacement. But if you are provided with an SOP expression and you are asked to realize the circuit using NOR gates only, you have to give the expression look of POS type expression, that means OR AND type expression. So this Y is equal to AB C complement plus A complement B complement C complement plus AC. So if I compute Y complement, that means AB C complement plus A complement, B complement, C complement plus A, C whole complement. Then it will change to POS form. Y bar is equal to A complement plus B complement plus C double complement, which will be equivalent to C. Similarly, A plus B plus C and A complement plus C complement. So, realizing the expression circuit for this. So, A is there, B is there, C is there, NOR using not using NOR, okay, and realizing the circuit A bar, B bar, C. So, this is A bar, this is B bar, this is C, NOR. Second one is A, B, C, this is A, this is B, this is C, another NOR. Then A complement plus C complement, this is A complement, this is C complement, another NOR, and all NORs multiplied using another NOR. But we have to keep this in mind that this is Y bar, this is not Y. So, to remove this complement from this Y bar, we will be requiring extra NOT gate in form of NOR. So, single input NOR will be equivalent to NOT. So, this will remove this complement and you will be finally getting the Y. So, in this way we can realize any expression, either it is SOP or POS, using NOR as well. So, we have completed all possible realization using basic gates, using NAND gate and using NOR gates. So, with this we come to the end of the today's lecture. Thank you very much.